Okay, next learning goal, folks, and this is going to be a familiar one from general chemistry. We're going to get into the Pauli Exclusion Principle and spin wave functions. So this will be a pretty short one, and it's going to set up a bigger set of videos that we'll digest. So recall, you've discussed the Pauli Exclusion Principle before from your Gen Chem days. Which, if you recall, states no more than 2 electrons, let's highlight that, no more than 2 electrons may occupy any given orbital. And if they do occupy the same orbital, their spins must be paired. And by spins being paired, that means one is spin up and one is spin down. Okay? And, obviously I don't have 2 right hands, but the correct orientation would be one is spinning with its requisite cross products in this direction, and the other is spinning in its requisite cross products in this direction. So recall from our module on rotations that we use quantum number ms to describe those, which are +1/2 and -1/2, stemming from the quantum number for fermions, which is an electron, S equals 1/2. So all fermions are particles with quantum spin number S 1/2. And so now ms is that range of S all the way down to S -1. So recall this vector has total magnitude S times S plus 1 square root h bar. And the projected magnitude on the z-axis, right, is given by ms h bar. So that's where electrons will always have either +1/2 h bar intrinsic spin or -1/2 h bar intrinsic spin. So as it turns out, this Pauli exclusion principle is a special case of the general Pauli principle. So this one is a special case of the general Pauli statement, which is when the labels of any 2 identical fermions, and so remember a fermion is a quantum object with spin 1/2, that's an electron. So when the labels of any 2 identical fermions are exchanged, the total wave function must change sign. So what that means is if we attempt to reconcile, which one is which, when we change its position, our wave function changes sign. And for ease of notation, I'm going to start writing our total multi-electron wave function as the following. Instead of saying R1, R2, where we recognize, right, those are the vectors describing the radial and angular positions of the wave function, I'm just going to replace those with 1 and 2 for ease of notation. And so, again, the general statement of Pauli says, if I switch those positions, I have to change the sign of the wave function, okay? So what this ends up doing is it creates a matrix of possibilities of possible spin states for any 2 electron system. And the 4 possible spin states that arise for any 2 electron system are the following. So we're going to call alpha spin up, and we're going to call beta spin down, and the 1 and 2 corresponds to the label of the electron. So we could have both spin up, alpha 1, alpha 2. We could have both spin down, beta 1, beta 2. And now we could spin pair them. So we could have alpha 1, which is spin up, beta 2, which is spin down. And now, because I don't know which is which, there's also the possibility of electron 2 being alpha. Oh, excuse me. I'm not editing that out. And electron 1 being beta. And because of that, because we don't know which is which, we're going to need a superposition to describe those spin states. So our generic spin state basis set will go as the following. will have some normalization constant, right? And it will be multiplied by the product of wave function 1 and wave function 2 plus or minus wave function 1 and wave function 2. So we create the possibility of having plus states or minus states. And remember, that's what Pauli tells us when we switch the labels, right? So now what that means is we will come up with the following basis sets. So we're going to have the sigma plus state, sigma 1, 2, where now this corresponds to the spin wave function. And that's going to go as the following. So the normalization constant for this two-term basis set is 1 over root 2. And then now that's times the following, alpha 1 beta 2, right? And then we could have plus, and then I'll just write it, I'll keep the positions in the same place. So alpha 1 now becomes beta 1, and beta 2 now becomes alpha 2. So that is one possible spin wave function. And of course, our other spin wave function is from switching the position, which changes the sign according to Pauli. So that's sigma minus spin wave function 1, 2. And we're going to have the same 50-50 normalization constant, right? 1 over root 2. And now that's going to go alpha 1 beta 2, same as we did last time, but now we'll say minus beta 1 alpha 2. And as it turns out, if we inspect both of these sigma plus and sigma minus spin wave functions, only one of them is acceptable to describe a pair. And as it turns out, then the other three that we have, right, 1, 2, 3, there's 4 of these terms, will describe spin antipaired, okay? All right, so we'll explore that in more detail in the next video.